Welcome back to ch205. Today I'll be talking about central difference and I'll show you one example of how to calculate the derivatives numerically using spreadsheet. So if you recall from last time, we talked about forward difference and backward difference. We talked about first order and second order approximation for the derivatives. And today we're going to look at the central difference. So in first order approximation, where the truncation of the Taylor series is in the order of delta x, that's why it's called first order, we do not have any central difference version. All we have is either forward difference or backward difference. If you want to do first order approximation, we have only two choices, forward and backward difference. However, if you want to do second order approximation, we have an option for central difference. And so in central difference, to calculate the derivative at point I, we subtract the function value at point I minus 1 from I plus 1, and we divide by 2 del x. So that is for the first derivative. And to calculate the second derivative, we need to know not only the function at point I, but also the function value at I minus 1 and I plus 1. So as central difference stands for, if we want to calculate the derivative at point I, we need to know both points, the points after xi and the point before xi. And basically in this case, xi is at the center of the distance between I minus 1 and I plus 1. Same thing with the first derivative. If you want to calculate the derivative at point I, we use function value at point I minus 1 and I plus 1. The center of this distance between I minus 1 and I plus 1 is xi. And that's why it's called central difference. All right, so let's look at one example. Well, actually, before getting to the example, I want to take a few minutes in talking about partial derivatives and how we can calculate that numerically. So far what we just looked at was f only function of x. But what if f is a function of x and y? And we want to take derivative or partial derivative with respect to x only. Okay, so in equation 4.12, we look at the derivative with respect to x of a function f, which is a function of x and y. Okay, if you want to take derivative with respect to x, we can just apply forward difference or backward difference only on x and keep y fixed. So as you can see here, we are changing x to x plus delta x and subtract x from it, but we are not changing y at all. So in both the first and second term, y is always fixed. And then we divide this difference by delta x, because the difference between the two x values, right, between x0 and x0 plus delta x, the difference is delta x. That's why we divide by delta x. This approach is on the order of delta x, and it is called first order approximation. It is a forward difference because we're using the point after point xi to calculate the derivative at point xi. We can do central difference. So this is the central difference version of the partial derivative with respect to x. Because this is central difference, we have to use the 2 points on the sides. One on x plus delta x and the other one on x minus delta x. Subtract the 2 and we divide by 2 delta x. That is going to be an approximation for the first derivative. Okay, so this is the central difference. We can also have backward difference. So to calculate the derivative at point x, we subtract the function value at x minus delta x from x, right? In all these cases, y naught is always fixed. We never change y naught, okay? We always change delta x and x, and as a result, these will be derivative or partial derivative with respect to x. We can do the same thing to calculate the partial derivative with respect to y. In that case, we have to fix x. We have to fix x and vary y, right? Okay, so we can go to higher order derivatives, like in equation 4.13, we have the second derivative of f with respect to x, with respect to y, and with respect to x and y. So with respect to x, if we want to do the second order derivative, right, then if you don't remember that, we have to go back to table 4.1 and 4.2. Okay, so we are using second derivative. If you want to use first order approximation, we have one option for forward difference, we have one option for backward difference. So let me see which one this is. Alright, so this one we're using basically second derivative because, we're using central difference for the second derivative. And to confirm that, we can compare the first equation here with the second derivative using central difference. This is this one. So look at that, it's I plus 1 minus 2i and plus I minus 1 divided by del x squared. And that's exactly the same thing here. This is I plus 1, this is xi, and this is xi minus 1, and then divided by del x squared. So this is a central difference version of second order derivative. And that's also indicated here. So we can do the same thing to calculate the second derivative with respect to y. In this case, we fix x and change y. So that's going to be y plus delta y, and then y minus delta y, and divide the whole thing divide the whole thing by delta y squared. We can also do the cross derivative, like this one is derivative of the function with respect to x and y. So in that case, first we have to do the derivative with respect to x, and then we use that to get the derivative with respect to y. And if you do that, at the end of the day, what you get is something like this. We have two terms. The first term is you can group this one and this one. So in these two, we are fixing y plus delta y, and we are changing x from x plus delta x to x minus delta x, right? So in these two, we are changing x and fixing y. In these two, we are also changing x but fixing y, right? But between these two, we are fixing x and changing y, and between these two, we are fixing x and changing y. So this is basically looking like taking derivative with respect to x first, and then with respect to y next. So at the end of the day, what you get is something like this, okay? So this is xi plus 1, yi plus 1. This is xi plus 1, yi minus 1. And then xi minus 1, yi plus 1. And then xi minus 1, yi minus 1, right? So, and be careful about the sign. Whenever we have the sign difference between delta x and delta y, we get a negative sign. Like between this and this, we have plus delta x plus delta y. The signs are different, so the sign up front here is plus. But between this and that, the sign of delta x is changing, right? So here's plus delta x, here's minus delta y. And because of this plus minus, the coefficient here up front is going to be minus. And this one is the same thing, minus plus. The coefficient is going to be minus, and then minus minus. These are the same, the coefficient is going to be plus. All right, so let's look at one example here. Let's say I have a fluidized bed with a gas of density rho g, and the density of the solid phase or the bed is this much is rho sub s. You want to calculate the percentage of solid volume as a function of axial position. Okay, so the problem is actually how to calculate a function like this, where we have the derivative of p respect to z. The other ones are just a function, basically they're constants. We have these rho g and rho s from the problem statement here, no problem. The only thing is how to calculate dp dz. If this is the z, or axial position, and this is the p, how we can calculate dp dz. So just directly jump to the solution. Here is the table from the textbook. We have the z, we have the p, and now we're going to calculate dp dz. So let's look at the first value here. So I'm going to calculate dp dz here, but I noticed that I do not have any z, right? This is the z that I'm looking at. I do not have any z value before this 0, right? I don't have z equal minus 0.5 or minus 1. So in that case, I cannot use backward difference, because if I use backward difference, then the calculated derivative at this point requires the information of z value at minus 0.5, and also pressure at that z value. Because I do not have the z value at z minus 0.5, I cannot use backward difference. I do not have any knowledge on the back side of this point. So all I can do is use forward difference, because I know the function value at 0.5 and at 1. So both of these are actually ahead of x equals 0. So that's why we're going to use forward difference. Now for this one, we can use forward difference with second order approximation. If you look at the textbook, that table on page 83. So we're going to look at forward difference, and we're going to look at second order approximation. So it's going to be this, like minus 3 times the function at the current point, plus 4 times the function at the next point, and then minus the function at next point, divided by 2 del x, and that's exactly the same thing here. So that's minus the function value, or we can start from here, minus 3 times the function value at the current point, which is the purple cell, right? Purple cell is sitting at the same z value as the cell that I'm calculating the PDZ. Okay, the next term is 4 times the green cell, which is the next point, and then minus the blue cell, which is the next point. That's exactly identical to the equation on page 83. All right, and then divide by 2 del x, because my del x is the difference between two x values, or z values. Then del z is going to be 0.5, and then 2 times that is going to be 1. Okay, and this coefficient is, I think, for unit conversion. Yeah, so because we have kilopascal here, in dpdz we have Pascal, so we have to multiply everything by 1,000. Okay, so that's the forward difference. We can look at the next term. This is now, by the way, is central difference. So looking at the derivative at this point, we know that this is connected to this cell and that cell. So to calculate the derivative here, we're using the information on the back point and the point in front. So we're not using the function value at the current point, which is indicative of a central difference, because this point is the center of these two, and we are using actually the information on the back side and the front side only. Okay, and divide by 2 del x, because del x is 0.5, 2 del x is 1. Okay, so all other ones are forward difference, central difference, except the last one, which is backward difference. Now in this case, we do not have any point ahead of this. We have to use the information from the back side, and that is backward difference with second order approximation, which is identical to this equation. So 3 minus 4, 1, and we have the same thing here. 3 minus 4, and then plus 1 divided by 2 del x. Okay, So that was central difference, forward difference, backward difference. Thanks so much for watching, and stay tuned.